get series combination. Let's do the same thing for the parallel combination. So let's see which side is this. Okay, here. Now same thing as before. Let's look at parallel combination of resistors. Okay, so we'll say there's here a resistor, um, another one here, and another one here. Okay, you could have as many resistors in parallel as you like. We'll just, for now, just let's just look at three for simplifying things. So and you um, wait, before that, so we have this parallel combination of resistors. Let's say that this is going to be equivalent to, it's going to be equivalent to single resistor. Okay, a single resistor. Okay, wait, this is, so this is R, so EQ. So our combination is going to be equivalent to a single resistor. Or so this is R1. Let's say this is R2. This is R3. All right, and let's connect a voltage source, a cell or a battery, across this whole combination. Now, as by by definition, if for the parallel, sorry, not the parallel, the equivalent resistor, if we connect the same voltage source across it, okay, V, it's going to, so if this receives a current of I, this receives a total current of I, the whole combination, this single resistor is going to receive the same current I, okay, same current as what the whole combination receives. All right, so now let's do something similar to what we did before. Okay, let's find out that formula for, as we know, the current is shared, right? The current is shared for parallel resistors, right? And as formula, it is that your total current is going to be the sum of the in currents through the individual resistors. It's pretty simple. So if this is I1, sorry, no, this is I3. Sorry, if this is I1, this is I1. Um, this is I2, this is I3. All right. So what we'd have is I would equal I1 I1 plus I2 plus I3, right? Okay. Now let's divide by V. Let's divide by the value of this voltage source V. All right. So we'll have I by V is going to be equal to I1 by V, I1 by V plus I2 by V. Oops, my grip's getting loose. Okay, I2 by V. Okay, that's really not looking good. I'll try to make it better. Might have to take a break. So anyways, so we have I1 by V plus I2 by V plus I3 by V. All right. So doesn't look as obvious as what it was with the series combination, but let's look at something. Let's look at something. Suppose, say, for these individual resistors, as we said, the voltage for across all the parallel elements, okay, all the parallel resistors must be the same, and must be the same as uh, the total voltage right here, the one provided by the voltage source, the cell. Okay, so if this is V, the one across, the voltage across this has to be V, across this has to be V, across this has to be V, right? Okay, and well, if we just consider this resistor R1, what is its resistance? Okay, wait, okay. What does Ohm's law tell us? What does Ohm's law tell us? Tells us that the resistance is going to be the same, equal to um, V, okay, the voltage through it, divided by the current sorry, voltage across it divided by the current through it. Okay, it's all a mess. I often jumble up the words across and through. Anyways, so this is what Ohm's law tells us. This is what Ohm's law tells us. Now, something interesting. We have I1 by V in our equation, and we'd like to simplify that. Here we have V by I1. Okay, so why not just invert this? Why not just invert this? What we'd have is 1 by R1 equals I1 by V, right? I1 by V. Now this is what we needed. Okay, this is what it is in our equation. So this is going to be, oops, this is going to be, as we saw, equal to R1 by R1, the reciprocal of R1. Okay, same thing for the other two. I2 by V is going to be 1 by R2. I3 by V is going to be 1 by R3. All of them have the same voltage. Whoops, not I3, R3, R2. All of them have the same voltage across them, and the currents. This is I2, this is I3, so all is fine and well. So 1 by R1 plus 1 by R2 plus 1 by R3. So that's the right side. About the left side, what do we see? It's really the same thing as we did before, except this is your equivalent resistor. Obviously this is going to have, since the battery is only now providing the voltage to this one resistor, this will have a voltage of V across it. Okay, uh, and the current through it is I. So you have R equivalent, almost really the same thing as what we just did a while ago. So R equivalent is going to be V by I. Okay, but so what's I by V? If we invert, if we take the reciprocal of both sides, we get 1 by R equivalent is actually I by V, which is what's in our equation. Alright, so let's substitute that. We have 1 by R equivalent, 1 by R equivalent is equal to all of this. Alright, so this is our formula. Yahoo! So this is our formula for the equivalent resistance for um, resistors in parallel. Okay, for resistors in parallel, the reciprocal of the equivalent resistance is going to be equal to the sum of the reciprocals of the individual resistances. Alright. Okay, so and as I said, you could have as many resistors as you like in parallel. So if you have n of them, you'd take the sum of the reciprocals, sum of all the reciprocals of the n resistors. Okay, and then this would be equal to 1 by r, r sub equivalent. And this is something, when we are just first learning about parallel resistors, this is something we really need to be careful about when we calculate the value. Okay, because this is on the left side. On the left side, it's the reciprocal of the equivalent resistance. If we want to find the equivalent resistance, after finding a numerical value for the right side, we definitely shouldn't forget to take the reciprocal. Okay, we definitely cannot forget. Okay, so if we obtain some value here. Okay, suppose say 5. I'm just throwing that out. Okay, 5. Suppose say that was suppose say we got 5, okay, as the value here. Okay, as the value on the right side. Now we need to take the reciprocal. Okay, to find the equivalent resistance, we actually need to take the reciprocal. Okay, that's going to be 1 by 5, okay, ohms. So well, or whatever the unit is. So that's the thing, we cannot forget to take the reciprocal. And wait, I'll pause for a bit. All right, so as I was saying, yeah, we need to be careful about taking the reciprocal at the end of the calculation. And because of this, um, often people do write this formula in a different way. It's also convenient to do this if um, you know you'd like to directly just input the numbers in the calculator and not worry about anything. So uh, this can also be written as R1 inverse plus R2 inverse plus basically how many resistors in parallel you have. So this whole thing, okay, the sum of all the inverses are reciprocals, and then you take a reciprocal outside. Okay, this formula can also be written like this, and it's convenient in the way that you can just directly just plug in the numbers in the calculator and not worry about anything else, like you wouldn't forget to take the reciprocal at the end. But anyways, let's look at some problems. Okay, so I have one here. Let's see. So I'll be using the same values of the resistors that I just used a while ago, 1, 4, and 5, and I'll just fit them in parallel now, and you'll see that something interesting happens. So let's see. Here I have. Alright, I really need to get my grip. Alright, so here's one resistor. Here's one more resistor. I'm recording, right? Yeah. Okay. And here's one more resistor, and you have the cell. Okay, I'll use the same voltage as last time, 5 volts, right? And here you have, let's see, 1 ohm, 1 ohm, 4 ohms, and 5 ohms. All right, so basically again same as last time, we need to find the current. Okay, we need to find the current that's being provided by the battery to the whole combination, and for that we can uh, we can turn this into, okay, convert this to an equivalent resistance, okay, an equivalent resistor, and here we have some single resistance here, equivalent one, and same cell, 5 volts, same current has to be, as we said, I and well, what's your equivalent resistance here? So you have three resistances in parallel. Okay, so what you have is, let's see. So wait, 1 by R equivalent. Wait, R equivalent equals, so the sum of the reciprocals of the parallel resistances. So we have 1 by 1 ohm, let's write 1 by 1 plus 1 by 4 ohms, it's 1 by 5 ohms. All right, and this should give us, let's see, um wait, wait. So we have 1 by, well, it's just 1, and 1 by 4 plus 1 by 5, that gives you 29 by 20, that gives you 29 by 20. And if you take the reciprocal of this, we definitely shouldn't forget about that. So take the reciprocal of both sides, and you get the equivalent resistance is what? It's 20 by 29. 20 by 29 ohms. Alright. So if you want to do this directly in the calculator, you do something like this. So you have, sum of the okay, so open your bracket, sum of the reciprocals, 1 inverse, 4 inverse, plus 5 inverse, and an inverse outside, and then you'd get your answer. Alright, so anyways, this is my equivalent resistance, 20 by 29 ohms, 20 by 29 ohms. Alright, so the current is simply given by Ohm's law. So the voltage across this is the same as the battery's one, so 5 volts. So the current is going to be 5 V by R, so 5 by 20 over 29, and that gives me, let's see, um, 5 over previous answer, and that is 29 by 4, or in decimals that's 7.25. This is 7.25 amperes. All right, Now you might have noticed one thing. Uh, your We use the same resistors as last time, but your equivalent resistance is lower. It's actually much lower than what we got for the series combination, although we used the same values for the resistances. And well, we also got a high current because of that, obviously. But yeah, that is generally true, provided you don't have something like a short circuit, which we'll talk about in a bit. Okay, provided that your the a series combination is going to have a higher resistance than a parallel combination. Okay, well, I'll prove something neat in a bit, but before that, let's talk about that short circuit that I talked about, that I just spoke of. So let's say we have, and this is the same discussion as uh, what we did previous video, very similar discussion. So we have one resistor, we have another resistor, okay, and we have some cell right here. Okay, so don't really need the cell for this anyway. So if we have some some we have a short circuit, okay, in parallel with these resistors, right? So all all these three all these three are parallel. You could The short circuit is effectively, you could think about it as a resistor with zero resistance, right? So all these are in parallel. And what's the effect of this short circuit on the equivalent resistance? Now let's say this is R1, let's say this is R2, and you could have any number of other resistances in parallel, but just as you see, the short circuit has a pretty significant effect that it wouldn't matter what else is there. So but anyways, the intuition first, as we talked about in the last video, is this current right here from the battery. Okay, it wants to go along the path with the least resistance, and since this one provides no resistance at all, what will happen is all the current is going to pass through here. Okay, normally if you have some low resistance and some high resistances and all of them are in parallel, the maximum percentage would flow through here, but it's not like all of it would. But if you have zero resistance, so all the current, every electron would just like to flow through here. Okay, uh, there's no obstruction. Okay, I talked about it in the last video. All right, so and let's see how how equivalent resistance relates to that. So we have our equivalent resistance equation. So equivalent resistance equals 1 by R1 plus 1 by R2, and we have a short circuit. Okay, we have a short circuit. So 1 by R, okay, which is the value of the short circuit, and what do we know? It's 0, right? It's 0. So 1 by 0, 1 by 0. Now I know that there's I think I've been treating it a bit nonchalantly, but I know that dividing by 0 is undefined, and I cannot exactly put a value for this, but usually for these things, especially circuits and all, we just interpret it as infinity. Okay, and it does make sense. Okay, if you think about that, if you have zero resistance in like superconductor, you could say, and if you plug in and if you connect any voltage across that, you should get an infinite amount of current. Okay, that theoretically makes sense. So this is infinity, and again, no matter what, the provided uh, you have some positive numbers there, obviously, because resistance cannot be negative. So you have infinity plus some positive numbers, but that doesn't really matter, it would still be infinity. So what you get is R equivalent is equal to infinity. Okay, R equivalent is equal, sorry, 1 by R equivalent, the reciprocal of it is equal to infinity. Sorry about that. So R equivalent is actually going to be 0. Okay, R equivalent is actually going to be 0 ohms. So this is exactly another way to look at why uh, why there's going to be an infinite current here. Okay, because all the current is going to flow through here, and you have an equivalent resistance with 0, so infinite current. Anyways, that's still theoretical. um, all right, but the important thing here is that if you have any parallel combination, and as you'll see in the parallel combination problems, it's not like all the time you're just going to have a parallel combination and with a short circuit, and it's going to be an infinite current. If you plugged some, if you connected some series resistor with this, you need to actually care about what this resistance is. Okay. And for that, basically, what you just do is, so you have some resistors in parallel and there is a short circuit in parallel. You just say, okay, so the resistance of that combination is going to be 0. Don't need to care about that, don't need to do any calculation. All right, so that's the important takeaway here. If you have a parallel combination which includes a short circuit, okay, that's all, among the parallel components, your equivalent resistance is going to be 0, okay, every time. All right, so with that done, yeah, the other thing that I wanted to talk about, let's see, is, okay, so let's just put some context for this. This is going to be slightly mathematical, okay. It's not really something hard to grasp. Suppose say you have bunch of resistors in parallel, okay, bunch of resistors in parallel. So you have R1, R2, okay. I'll not draw the diagram for this just to save us some time. So you have uh, n resistors in parallel, okay, say, and suppose that R, okay, so R1, okay, suppose say that's your smallest resistance, okay. We could pick any one, like if you want to be really mathematically rigorous, you could say some resistance RK, R sub k, okay, is going to be the smallest. Anyways, the result is still going to be the same. So what I'm talking about is, let's set up an inequality. Let's set up an inequality. Um let's see. Let's have 1 by R1, okay, plus, okay, so wait, first thing, so I'll keep this on this side, on this side I'll also keep the same thing, 1 by R1, 1 by R1. Now, okay, so these two are equal obviously, but if I add some more things to the left hand side, like 1 by R2 plus 1 by R3, 3, all the way up to, all the way up to 1 by Rn, okay. So now what is going to happen, I added some positive numbers, right? All of these they're going to be positive, right? Because resistance is positive. Okay, I'll assume that there's no short circuit in any one of these, so all of these are positive, okay. um so these their sum is also going to be some positive number. So I'm adding some positive number to 1 by R1, so this is going to exceed 1 by R1, right? So, right, because I added some positive number, okay, so this is going to be greater than 1 by R1. All right, so um, that much is clear. Now, what is, does the left hand side look familiar, right? Because we have n resistors in parallel, and the sum of the reciprocals, as we know, is the reciprocal of, I'll write that here, wait, so it's the reciprocal of the equivalent resistance, right? It's the reciprocal of the equivalent resistance. All right, and this is going to be equal, okay, this is going to be, sorry, why am I saying it's going to be equal? So this is going to be greater than, I haven't really done anything with the inequality yet, so this is going to be greater than 1 by R1. Now, if I take the reciprocal of both sides, and we know that if you take a reciprocal of an inequality, you need to flip the sign. So if I take a reciprocal of this, what I get is R equivalent is going to be less than R1, okay. So I said that R1 is the smallest resistance, but you could also say it's any resistance, okay. So there's a couple of ways to say this. You could say that the equivalent resistance is going to be smaller than any individual resistance, okay. And a more stricter statement, what we derived here, okay, we basically proved both really. Okay, so stricter statement would be that the equivalent resistance has to be less than the smallest individual resistance, okay, in the parallel combination. So I'll write that down. So um, the equivalent resistance. Oh, whoa, oh, that's big. Let's see. All right. So the equivalent resistance must, um, again, I'll assume that there's no short circuit. And what happens in, when you have a short circuit is obviously you get a resistance of zero, an equivalent resistance zero, must be less than the smallest individual resistance. Individual resistance. Okay, for a parallel combination. Okay, for a parallel combination. All right. So this is I think it's a pretty neat result. And what I usually what I do what I use this for is checking my answers, or just to feel a bit safe about them. So what I'm talking about it. Wait, where is it? So let's see first. Um, right, so what I'm talking about is, suppose say you have some problem. Okay, you have some problem. There's a parallel combination in it, and suppose say your resistances are 3 ohms, 5 ohms, okay, say 9 ohms. There might even be other, any number of other resistances, okay, parallel. So, but suppose say you got an answer, okay, after doing a calculation, to find the equivalent resistance, you got an answer of 4.1 ohms. Okay, now is this possible? Well, no. Okay, um, you have 3 ohms. Okay, this, as as far as we can see, it's smallest, but it even that doesn't even matter. As I said it, your equivalent resistance has to be less than any resistance that's in the combination. Okay, any resistance, even the smallest one. Okay, so 4.1 ohms is definitely not possible. Okay, uh, at the you need something less than 3 ohms for it to even be viable as an answer. All right, so that's something that I think is a neat result, and helps me to be sure about my answers. And I think, okay, so this is also something cool. So I think it should also make intuitive sense, because as I did in the last class, like, if you have, say, if you have a road like here, okay, so, and well, it splits in whoops it splits into three roads. Okay, it's you have three roads. Okay, so obviously it should make sense that um, the obstruction, okay, so suppose that this is the 3 ohm road. Okay, just saying, this is the 5 ohm road, and this is the 7, this is the 9 ohm roads. Okay, so uh, just think about them as, maybe there are 3 boulders here, 5 boulders here, 9 boulders here, some obstructions. But if this has some obstruction, uh, altogether the 3 of them, you have 3 paths to choose from. Okay, 3 paths to go. So you should face less obstruction as a whole, right? Overall you should face less obstruction overall than, if you were just limited to choosing any one path, right? If you were just, suppose say, just strictly told to choose this path, um, you'd have more obstruction, right, than if you had choice to choose from 3 paths, right? All right, so uh, that's why the resistance, okay, you can think about the vehicles as electrons here. That's why the resistance is actually lower. Okay, the equivalent resistance is lower than any one of the individual resistances. Okay, so uh, less traffic overall than if you were limited to just one road. That's an analogy. All right, so that's done. Let's see. Next